As higher frequency bands are used in 5G, weak coverage areas are more likely to appear due to factors such as propagation loss, wall penetration loss, and interference during signal transmission, affecting user experience. In addition, as the transmit power of user equipment, UE, is much lower than that of a base station, uplink coverage becomes a bottleneck. Therefore, how to improve uplink coverage is a key challenge for 5G. Turbo Uplink is a Huawei proprietary technology to improve uplink performance. By using an industry-leading high-performance receiver and adaptation algorithms oriented to high-power UEs, it improves uplink coverage at edges and expands uplink coverage significantly. The high-performance receiver of Turbo Uplink improves uplink user experience by using more intelligent scheduling policies to increase transmission rates, more accurate spatial channel estimation to reduce interference, and more accurate antenna selection to improve useful signal quality. Frequency selective scheduling under weak uplink coverage. As the transmit power of UEs is a constraint in weak coverage areas, their uplink coverage can be improved by reducing the number of RBs to increase the power of each RB. Based on the frequency selective characteristics of channels, the SINR of UEs can be increased by scheduling UEs on certain RBs and more data can be transmitted. Frequency selective scheduling under weak uplink coverage is introduced to attempt to increase the number of RBs and the transport block size, TBS, so as to increase the uplink throughput of UEs under weak coverage. Spatial channel estimation under weak uplink coverage. In interference scenarios, the performance of channel estimation is relatively poor. Spatial channel estimation under weak uplink coverage is introduced to minimize interference signals and retain useful signals, increasing the SINR and uplink throughput of UEs under weak coverage. Closed-loop PUSCH antenna selection. Different terminal grips and antenna positions result in different channel environments. Using a fixed antenna for PUSCH data transmission may not achieve the optimal performance. Closed-loop PUSCH antenna selection is introduced to improve performance. Based on the uplink SRS measurement result, the base station determines the optimal antenna. Through the PDCCH, it instructs the UE to use this antenna for PUSCH data transmission. Then the UE switches to the optimal antenna as instructed, increasing the uplink throughput when the UE is under weak coverage. To further improve the SINR of UEs and fully utilize the capabilities of high-power UEs, improving uplink user experience, innovative power adaptation algorithms are introduced for Turbo Uplink. Uplink waveform adaptation. 5G supports cyclic prefix OFDM, CP-OFDM, and DFT spread OFDM, DFT-S-OFDM in the uplink. What are the characteristics of the two waveforms? CP-OFDM can use non-contiguous resources and allocate resources flexibly in the frequency domain. However, it produces a higher peak-to-average power ratio, PAPR, after superimposing multiple subcarriers in the time domain, limiting the transmit power of UEs. DFT-S-OFDM can use only contiguous resources in the frequency domain. However, it produces a lower PAPR and a lower maximum power reduction, MPR, as there is only one subcarrier in the time domain, enabling UEs under weak coverage to transmit at higher power. How does a UE adaptively switch between the two waveforms? If the base station detects that the UE is under weak coverage, it instructs the UE to select DFT-S-OFDM to reduce the PAPR and transmit at high power. Otherwise, it instructs the UE to select CP-OFDM. Uplink half-pi BPSK modulation power boost. In traditional modulation schemes, the PAPR of UE signals is high. If the transmit power is increased, signal distortion occurs. As a result, the transmit power of a UE can reach only 23 dBm. Uplink half-pi BPSK modulation power boost is introduced to address this issue. By utilizing uplink half-pi BPSK modulation and DFT-S-OFDM, both of which have a low PAPR, this function reduces the PAPR of PUSCH and DMRS for UEs of power class 3 under weak coverage. In this case, signals are not prone to distortion after power increase, and the UE transmit power can increase from 23 dBm to 26 dBm, improving the uplink coverage performance of UEs under weak coverage. full power dual transmission. The maximum transmit power defined for Power Class 2 is 26 dBm, according to 3GPP Release 16. Full power dual transmission is introduced to implement transmission at a maximum of 26 dBm. Specifically, it allows the UE to use one PA for transmission at 26 dBm or two PAs with each for transmission at 23 dBm to improve uplink coverage. That's all for the main functions of 5G Turbo Uplink. For more information, scan the QR code on the screen.